Now let's look at Bernoulli's equation, which is one of the most important concept in fluid mechanics, which is used extensively in various engineering industries. So you need to understand this concept really well. Bernoulli's equation is basically says that the energy is concerned. The intrinsic energy, that is the energy in the fluid, right, or potential energy due to the height. The other is the kinetic energy, which is due to the movement or the velocity. The pressure energy, the fluid of the pressure can do the work. So those are the three intrinsic energy. The extrinsic energy is the frictional loss. The mechanical energy added by the pump, that is our interest, right? Sizing a pump or a fan. The heat energy in heating or cooling the fluid, the thermal energy can be considered, but we are going to ignore in this text. For most application it holds true. Unless there is a huge temperature difference, the thermal energy is relatively negligible. So let's go through each one term, the potential energy. The potential energy is mgz if z is the height. So if you raise the fluid to a height, it has a certain energy when it can do the work. For example, in the Niagara Falls, when the water is at the top of the area, it has a huge potential energy. When it is falling down, it's being converted to the kinetic energy, which you can extract it out in the hydrothermal energy, right? The second is the kinetic energy, which is given by half mv square or the u square. So due to the velocity, it has a kinetic energy. The next is the pressure energy. The pressure times volume is energy. For example, the pressure is Newton per meter square, volume is meter cube, so that gives you Newton meter, which is the joule. So it's kind of like your ideal gas law, right? PV is equal to nRT. So PV is the energy, pressure energy. The frictional loss is the next one, which we slightly look it up on the last one. The F in the pipe, do you remember the F in the pipe? The frictional loss, the delta P, is a function of F. We did go through the procedure. 2F into L by D into U square by rho, right? That's in pressure. You could convert it to the energy form, that will be the frictional energy loss. This is the major pipe flow. There is also minor pipe flow, which I will refer you to watch the author's videos to understand much more. The second is the energy added by the pump. That you may need to consider. So the other effects are the thermal energy, which we are going to ignore. And we are going to assume that the rho is constant, meaning that the fluid is incompressible. It even works very well for the air when it is blown through the heating and the air ventilation systems. So it's fairly good. Then you can assume the density as a constant unless you are using like a compressor or something like that. So what does Bernoulli's equation say is, if you have a continuous stream of fluid, okay, and let's say at some point you have a pump, okay, and then you are pumping to some level and you have a liquid in one here, okay, so any point A, and you can pick any point B, the total energy in A is equal to the total energy in B as long as they are continuously connected by the streamline. So you need to consider the pump energy added. You need to subtract out the frictional energy, and the total internal energy A and the B compensated for the added energy and the lost energy due to the friction should equate it out. So that is the Bernoulli's equation. Note down that in this one, each of the term has the units of joule. This is not a most common form, okay? So in case, if you say that if the height of the two location is the same, Z1 equal to Z2, you can cancel out, right? If the diameter of the two pipes are the same, then the V1 equal to V2 you can cancel out. If they both are exposed to atmosphere, okay, you can ignore pressure. Then in that case, the sizing of the pump, the energy required by the pump should just be able to overcome the friction. Okay. I also just want to let you know that some people use the term W for EP, W for the work added. Some people use capital F for EF, which is the friction. Okay. But as long as you understand the concept, you can, even if people use the different notations, you should be able to understand it. But suppose if we consider for simplification purposes, there is no pump between point 1 and point 2, you can ignore it. And if you assume that there is no friction, it's a smooth frictionless pipe, you can ignore that. Then in that case, the potential energy plus kinetic energy plus pressure energy is constant throughout the fluid. That's the Bernoulli's equation. The energy is conserved. If we divide the previous equation by the mass, that is joules per kilogram, you get this equation. Okay, so you can note down that PV by M is equal to M over V is the density, so we convert it to P by rho. Okay, so each term has a unit of joules per kilogram. Okay, but the most common form is the head form. If you divide it by the gravity, the previous form, so if you divide the previous equation by gravity, G, then you get Z1, which is the height 1, times V1 square by 2G plus P1 by rho G equal to this. So this is commonly called as a potential head. This is known as the velocity head. This is the pressure in the units of meters of the fluid column. So all the units are in the meters of the fluid that is considered in the system. Okay. So this is the most common form which you might have studied in your fluids class too. The another one is a pressure form. Okay. So if you take the previous equation, if you multiply rho G to the previous equation on all sides, then it's the rho G Z is the potential pressure this is the velocity pressure. This is just the pressure. They are all in pascals. So you have to really understand that the velocity can be mentioned as a velocity pressure or a kinetic energy or a velocity head or the velocity energy. So could be confusing, but it's basically you need to understand all these relationships. And if you look at here, the pressure is equal to rho gz. We studied earlier, right? Rho gh, right? So if you have a height of a liquid column, if you want to convert it to Pascal, pressure is equal to rho gz. That's what it's the potential pressure. Okay? So you need to be aware of this. So if I tell that like a velocity pressure, velocity energy, velocity head, you should know what the term means. The easiest way to understand is, look at here, that's in pressure. We know that. So all other terms have been accordingly rearranged. This is the head. We know that this is the head in meters. So all other terms were rearranged accordingly. And this one is the joules per kilogram, which is not that commonly used, but the author does use it. And this is the energy form. We all know that like a half mv square and mgz are the energy terms. So you should be really conversant in using these different terms, the potential energy, the kinetic energy, and pressure energy in all different forms, either as the head, energy, pressure. You should be able to quickly be able to convert between each forms. So that concludes Bernoulli's